So firstly, let me start by thanking Professor Bagchi for giving me this opportunity, Professor Chandra for getting in touch and getting me to know about this, and of course Rajiv and team at IIT Tirupati for organizing this.
Yeah,
So
Amolindu played a big role, but as always, he kind of keeps low profile. Yeah. Okay. Right.
So I am going to talk about Schrödinger equation in the age of AI, and let's see how I can place my talk as such after two really nice and illuminating talks by Professor Ray and Nishant. Okay, so yes, let me get a pointer. Okay, so I'm actually a quantum chemist, and my interest in solving the Schrödinger equation comes from molecular systems. So, to solve chemistry, to solve more importantly, excited state chemistry, let's say ask questions such as important in electronic spectroscopy, in some kind of processes in biology that involves light matter interactions, or some kind of an energy transfer process. Or for that matter, sometimes there are spin-spin transitions that are present in some material systems. So whenever one asks questions like that, they have to understand the energetics of the ground state for sure, but also the low-lying excited states. It could be excited states as in electronic excited states, it could be excited spin states or anything, depending on the phenomena that one is interested in. So that essentially brings us to the Schrödinger equation, which has been shown from the first talk onwards. And I'm not going to go into the details of the Schrödinger equation as such, but I would like to note this quotation by Dirac, that the fundament he mentioned as way back in 1929, that the fundamental laws necessary for the mathematical treatment of a large part of physics and all of chemistry are completely known, and the difficulty lies only in how to apply these laws and how to solve these equations. And it so happens that that difficulty has still not kind of let up. We still have a thriving community who is trying to calculate um, um, energetics and phenomena that are important in chemistry, biology, physics, and so on. And I will show you why it remains so challenging even to this day, 100 years, almost 100 years from this quotation. Okay, so what happened? Okay, so if I want to set up the molecular Hamiltonian without going into the details of the Schrödinger equation, which has already been talked about, let's say if I have a hydrogen atom problem, of course, in our college textbooks, we already have how to set it up. We basically have the kinetic energy and the potential energy. And here, since I have only one electron, I can just transfer the center of, I can center my frame of reference on the nuclei and therefore have only one coordinate of importance. Let's say if I have a H2 plus, which also has one electron, but now I have two nuclei, then the equation will start looking a slightly more complicated, but still nothing too difficult to solve. Which the moment you have something like a H2 molecule, you have quite a few terms coming in. I will tell what each of these terms are. Essentially, this is any molecule, and of course that will have the kinetic energy of the electrons, the kinetic energy of the nuclei, each of them, the Coulomb interaction between two electrons, so that's going to be the repulsive force, the Coulomb repulsion between two nuclei, and the Coulomb attraction between an electron and a nucleus. So as such, this equation looks pretty reasonable to set up, but I'm sure fairly daunting to actually compute anything out of. So first, what one would do is get rid of the time dependence. So that's essentially the methodology that somebody in electronic structure theory would follow. They would get rid of the time dependence of the Schrödinger equation, and we would arrive at the time independent Schrödinger equation. So I will just have a Hamiltonian, and I will try to find its eigenvectors, eigenvalues, and so on. And ideally the lowest few, not all. And second assumption that I will take is basically to understand that the nuclei is much, much heavier, even if it is hydrogen nucleus. That one is also much, much heavier than the electron. So I'm going to take the Born-Oppenheimer approximation, which says that the nuclei are stationary in the time frame of the electrons. So that's a pretty reasonable approximation to take. And that brings us to the electronic Hamiltonian, whereby I have gotten rid of the nuclear kinetic energy, and I could also somewhat get rid of the nuclear repulsion in the sense that that's a constant. So, when I have a differential equation and I have a constant attached to it, that's not going to do much. I can just keep it aside and then add on that term in the end. So the green term over here is the nuclear repulsion, which I'm going to, keep aside and not use when I actually solve the molecular electronic problem. So the terms that I still have to deal with as an electronic structure theorist is the first three terms. In the first two ones, you will notice that the summation is over a single electron index. So that includes the electronic kinetic energy. So of course, each electron by itself and their kinetic energy. And this is the energy of the nucleus that the nucleus affects, how the nucleus affects each of the electrons. So I'm summing over all the nuclei. And given that the nuclei I've taken is fixed, in this fixed nuclear approximation or Born-Oppenheimer approximation, I know all of the RIAs at that instant. So with respect to the electrons, I can just sum over all the electrons and I have the one electron terms. So those are referred to as the one electron terms, which is the kinetic energy and nuclear attraction. So electron nuclear attraction. And the second term is what causes all our pain. And that is the reason why electronic structure theory remains a thriving and developing field even today. It is the electron-electron repulsion. There are two electronic indices at once, and therefore it becomes a set of coupled differential equations whenever I'm thinking of this full Hamiltonian and its solution. So I can't solve one electron at a time, like I solved for the hydrogen atom problem. We did it in our textbooks or courses and stuff like that. So that's where all the problem arises from. And so the way that, of course, electronic structure theorists are doing something. So how are they doing that? If that's not exactly solvable, we immediately pivot towards some approximations. And the first approximation we take is, let's say there was no correlation. Actually, we do not take no correlation, we kind of take an average correlation. Instead of this yellow term explicitly, we take some kind of an average field that is applied on each electron. So if I do that, then I can write the really complicated, whose form, of course, I don't know, nobody knows what is the wave function of a molecule, which depends on all of the electronic indices. Instead of that complicated form, I can just write it as a product. And of course, I can't make it just a product because I have to follow the rules of antisymmetry. So I antisymmetrize and keep all the molecular orbitals in a product form. This is essentially our most favorite molecular orbital theory. And when you solve this, what we get is the Hartree-Fock theory. So what I have arrived at is essentially not this many electron picture. So I have not taken all the electron repulsions explicitly. I have taken kind of an average field effect or a mean field approximation. And in that mean field approximation, I have written out the wave function as this form. And in that form, I'm trying to solve the molecular electronic Hamiltonian. There is an alternative way to do it, which is the density functional theory, where instead of just taking an average, we also take a functional form, which is See, the Hohenberg-Kohn theorem says that there's an existence of a density functional, but nobody really knows what that functional is. So people have come up with many different exchange and correlation functionals, which is what you know, the different DFT functionals that you have come across, whether that be B3-lip or PBE or omega B97, so on and so forth. So with these different functionals, people have basically given different mean field approximations of how the interactions might look like. Again, that is not a true many-body interaction picture. And of course, it's not the true many-body perspective. It is actually far away from the many-body perspective. So we'll see how good or how bad we would do if we, didn't add in anything else to it. Okay, so of course we do not leave the mean field approximations just as is, at least in the ab initio picture where we start from the Hartree-Fock theory. We either add in the rest of the correlations using what is known as configuration interaction. Configuration interaction means instead of just one configuration of the electrons, we take all possible configurations. So you might say, I want to calculate the ground state. Why will I take all of these configurations? The idea actually lies in a mathematical concept that any function, and I mean any function, so of course also the wave function, can be expanded in a complete basis of functions. These are eigenfunctions of that Hamiltonian in the mean field basis. So these eigenfunction basis or the molecular orbital basis, if I take all functions in them, they will form a complete basis. So I can expand my wave function in that basis. That is the mathematical logic that goes behind why configuration interactions would even work. Okay, so that's one way to do it. And I will show you why this is, I have already told why this is done, but I will show you the computational cost of it, which is brutal. The other approaches are, of course, perturbative. So you can either use second order, third order, fourth order, nth order perturbation, or you can use something like a coupled cluster theory. So these are basically how you kind of add in the correlation, which you originally did not consider properly because you had to start somewhere. Okay, so let me kind of first give a computational scaling of what exact scaling. So exact all the configurations if I added in, so the full basis, if I did that, then I would definitely be able to solve for a molecule such as water, which is great. Benzene may be just about. For any other bigger molecules with at least decent basis sets, I would not have a fighting chance to compute. On the other hand, if I take a second order perturbation, I can go probably up to a molecule that is like a cholesterol or something like that, but still not proteins and big material systems and things like that. So we are still falling short. That is with respect to computation. Now let's see how far we can do with respect to accuracy. So here I'm again going to go back to a very small molecule, water, and try to pull its bonds apart. So I'm a chemist, I need to break bonds and make bonds. So if I pull it apart and if I do a full CI, which as you saw in the previous slide, I can afford to do for a water molecule, there the full CI gives a nice exact result. In other words, when I pull it apart, what should the total energy go? It should smoothly go to the energy of one oxygen atom and two hydrogen atoms, right? Just the radicals, just the atoms itself. On the other hand, if I did a second order perturbation MP2, this weird red curve is what it would look like. And if I do coupled cluster, this blue curve is what it would look like. DFT would be even more atrocious. I didn't want to show it. So if I plot out the errors with respect to the exact or full CI calculation, this is what it looks like, which means that at infinite separation, so at the bond breaking limit, I essentially have an infinite error, which is terrible. So how do I do chemistry with it effectively? And this effect that I have shown over here shows up in excited states. So if I were looking at some electronically excited, spectroscopic quantity, I would run into the same problem if I were looking at polyradicals, transition metal complexes, polyenes, graphenes, metal clusters, pretty much anything interesting in chemistry, if I were looking at, I would run into this problem in some way or the other. But because we are in certain regimes of the reactions where this does not come across as terrible, we still use DFT. I am not trying to say that those methods are useless. I'm just trying to say that there are regimes where those methods are severely limited. So there is need for developing new real many-body approaches. And what is the cost of those real many-body approaches? That is indeed exponential. I will give a simple toy example why it is exponential. So I have those orbitals, right? And I'm going to make functions out of all possible orbitals. So one way to do that is to just look at spin systems and see how many ways I can put spins. That will basically give me an idea how many ways I can put electrons in orbitals. So if I have one such site, I have two ways of putting spin up, spin or down spin. If I have two such sites, I would have four such ways. So like this, down, 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 up, so on and so forth. Now, if I have three, I will have 2 cubed or 8 such possibilities. And therefore, if I have n such sites, it will basically become 2 to the power n scaling. So that is an exponential scaling that will kill us very quickly. Here I have the plot of 2 to the power x just for fun. So this, the exact correlation, if I were to get in this molecular orbital basis, that would scale exponentially. But really, is this problem exponentially hard? That's a question that deserves to be asked. And in fact, the answer is not. Because people have looked at the quantum information and the sparseness of the Hamiltonian matrix and the sparseness of the wave function. So one easy way to think about it is that the Hamiltonian only has one body and two body terms. So if you look at all the connected terms, so all the off diagonal terms, if they are very far away from the diagonal, they essentially become zeros. And therefore we have a very large matrix, sure, but that matrix has many, in fact, too many zeros. So the total amount of information that is present is low, while the way of expression that we have of our traditional many-body wave function theory is very big. So we need to somehow pack this data into smaller space and in a meaningful way. And just to kind of reiterate, this is the exponential wave function, the exact wave function, and this can be written in the occupation number formalism as this. So these NIs are the occupations of each orbital, and this is the coefficient that is that says how much of this configuration is important. Okay, and this is the matrix product state way of looking at this this kind of a wave function. So basically, this is an n dimension. This psi is essentially an n dimensional tensor. So each of these legs that you see, these are dimensionality of a tensor. So in each direction, you have some 4 numbers, but if you have n dimensional such tensor, then it will have 4 to the power n objects in it. So that's the problem. Now, on the other hand, we know of mathematical concepts such as eigenvalues or singular values. And since this is a very, very rectangular object, a tensor is an object after all. So that tensor can be decomposed into lower rank tensors. So how would I do that? I can perform a singular value decomposition. And if I do that, I can break this up into a matrix multiplied by this diagonal matrix multiplied by another tensor which has one less dimension. So if I keep doing that over and over again, essentially I will have a matrix multiplied by a 3-dimensional tensor, multiplied by a 3-dimensional tensor, and so on and so forth. In the mathematics literature, this is referred to as tensor train. And in the physics literature, this is referred to as matrix product state. Matrix multiplied by matrix, so matrix product state. Although these are actually tensors. That's why the mathematicians' way of saying it's a tensor train. Anyways, notwithstanding what these are called, if you look at the dimensionality of the problem. To begin with, it has the dimension of t to the power n. Now, if you think each of these objects will have one leg, another leg, another leg, so three of them. So the total dimension is basically d times m squared. M being how many of these singular values I have retained. See, all degrees of freedom are not equally important. That's exactly what I mentioned when I said that information, there was a lot of this was a sparse matrix. Information was not so much. So I can leave a lot of these singular values and still be able to get the most important data out of it. So that's the dimension of each of these objects, and there are n of these objects. So from an exponential scaling, now I have made an object that is linear in scaling. So in some way, therefore, matrix product state is a fantastic answer, which gives us a form of a wave function which is very compact. And there in the 2016-17 onwards, what was observed first by this paper by Carleo and Troyer in Science is that there are basically tensor networks are equivalently expressible as restricted Boltzmann machines, and then later on it was shown that by deep neural networks. So that's basically where people realized that instead of solving these problems variationally, one can solve for these problems in a machine learning and AI based way and actually be able to train and find the wave functions. See, I'm not only training and finding the energies, I'm actually finding the wave functions using a neural network or a restricted Boltzmann machine kind of a framework. Just to give, so we have our work over here, and I'm just going to briefly explain the idea behind it, which is essentially what is used throughout in all the work. So the idea is now I have a wave function, which I don't exactly know. My idea is to find this wave function. So I have express this wave function as some kind of a weight factor multiplied by by what is the occupation number of that configuration. What I need to find is this weight. The moment I find the weight, I will be able to find this f of x. So instead of minimizing this w with respect to energy, which is what variationally we do, we can find this w with respect to some data. And this f of x, we can take literally any full basis function form, and that basis could have been the molecular orbital basis as before, or it could be a neural network for function of a functional neural network form of those molecular orbitals. So that's also a very reasonable basis to take. And using that basis, you can essentially find out these W's from some kind of a data-driven approach, which is what we have shown. I'm not going into the details, but I'm just giving you the motivation of why work like these are necessary and indeed possible. Another way that machine learning is used in this field a lot, and this is what Nishant talked about in his lecture to some extent, it's basically to find force field, machine learned force fields. Here the approach is slightly different. So here in these machine learned force fields, people endeavor to learn the energy and the forces. They don't really endeavor to learn the wave function, which has a lot more data than just one energy and force, which is basically a 3 dimensions. So that's what there's been significant work that has gone into energy and force finding in the field of machine learning force field. There's this Annie force field, which is very popular. There's also a lot of work on water force fields by Francesco Paesani. There's a lot of activity and very good activity going on in this direction. I will not talk about this because this was already touched upon in the last lecture. Another problem that arises when one talks about chemical reactions, quantum chemistry, is the size of the chemical space. If somebody asks you the question that I want to find a suitable solar cell material, or like we are doing right now, I want to find a suitable singlet fission material. The problem is the size of the chemical space, as in on what kind of a space am I going to search for this suitable candidate? Because the total chemical space is of the order of 10 to the power 60. And this is what I had seen in a kind of a magazine in 2020 or so, that the size of chemical space of small to medium molecules is 10 to the power 60. So there are that many molecules. I can't afford to calculate quantum chemical calculations on even a fraction of those 10 to the power 60 molecules. So how am I going to find suitable candidates in what space? So the problem in computational chemistry, therefore, can boil down into different aspects. One is that the chemical space is infinite, or maybe exponentially large is a better way of putting it. On the other hand, quantum chemical calculations, as I have mentioned before, are slow and become very slow if they are for larger systems and if you are trying to do accurate calculations and so on. And ideally, we would like to know electronic properties of molecules, very high accuracy properties such as spectroscopic properties, magnetic properties, and so on. So how do we even begin to crack this ginormous problem? There's actually, again, reasonable amount of work going on in the direction of chemical space exploration. And here is one representative work from the group of Graham Day, where they have basically created some library of fragments. And from those initial population, they generate new molecules that resemble the space before, and they kind of expand and test those molecular space and have a fitness function to keep whichever. So basically they have a fitness function that depends on various criteria. One is what is the stability of the molecule. Second is what is the how easy are those to synthesize, and then finally whether they are even good candidates for whatever they are trying to find. For example, here they were looking for organic semiconductors. So there's actually a reasonable activity in this direction that is going on. In fact, in TIFR Hyderabad, Raghu Ramakrishnan is doing very good work of mapping out the chemical space of various different classes of molecules, and thereby giving very detailed information about the chemical space exploration and how it should be done. And I will finally end with this one of our own work, where we had looked at the chemical space of melanin being the brown-black pigment in the human body. And the question we were asking is, what is the origin of the electronic spectra of these melanin molecules? And the way we had done it is we had kind of broken up the problem into two steps. One is, of course, how to combinatorially generate these different kinds of melanin species, melanin-like species, melanin-like chromophores from combinatorial techniques, then have a nice or rather compact way to describe it to a computer, because I will need descriptors which are compact, which are useful, so that it can predict some property. And the property being here, what was the spectra of each of these different fragments. And then we kind of did a reverse mapping of, then if I ask the question, what kinds of features of molecules is responsible for certain spectroscopic characteristics, we could pinpoint those. And we can now predict melanin-like chromophores that are responsible for excitation in different parts of the visible and UV spectra. With this, actually, there is no much conclusion to this, because work in many groups, including ours, is ongoing in this direction very actively. So I will not have a conclusion, but I will thank my students whose few work I showed, but of course, they always give us, encouragement to do interesting stuff. So thank you.